One thing that we often want to do in applications is when we have a linear map, we will often, for various reasons, want the inverse of that linear map. Of course, not every linear map has an inverse. If it does, of course, that means it has to be an isomorphism. But that sort of leads us to the question, if we have a linear map represented by a matrix, what is the matrix that represents the inverse of the linear map, if there is one? So the situation here is if we have V, a map H to W, with an appropriate basis so that we have a representation. V is going to be isomorphic to some Rn. There's some matrix, which I guess we could call capital H, that represents this. This is going to go to Rm. If there is an inverse, the inverse function will get us back to V. On the representation side, we're going to get back to Rn. And the composition from here to here should be not just an isomorphism, but actual equality, right? Or I should say the identity map on V. So starting in V, doing H, and then H inverse should get you back to not just the same vector space, but the same vector. So, H inverse of H of any vector V, little v in capital V, should be equal to the identity vector on little v, which is just going to give you V, right? And also the corresponding thing for W. If you start in W and do the inverse and then do H, you should get back to where you started. But the question is, in this setup, what matrix is going to show up right here? How could we calculate that matrix? What properties will it have, etc., etc.? Well, since we don't know what to call this right now, let's call it G, I guess. We know that composition of linear maps corresponds to multiplication of matrices, right? So up here, the composition of H and H inverse is supposed to be equal to the identity map on V, and that means that the matrix that represents the inverse times the matrix that represents the original should be equal to the matrix that represents the identity on V. Now, if you let yourself choose any base for this copy of V and this copy of V, there are many different matrices that could represent the identity matrix. But if you use the same basis for both the domain and codomain version of V here, then the matrix that represents the identity function will be the identity matrix of the appropriate size, which in this case is going to be n, I think. Yeah, n. So what we're looking for a matrix that represents the inverse linear map is a matrix that, when multiplied by H, gives you the identity matrix. And the name for that sort of matrix is, of course, an inverse. So an inverse for a matrix A is a matrix B that satisfies these two equations. A times B should give you an identity, and B times A should give you an identity matrix. These identity matrices should both be whatever size is appropriate to make this whole thing possible. Although, if this linear map is invertible, so that the matrix H has an inverse G, then that means H is an isomorphism, and that means that N and M are actually the same. So the only way an inverse could exist is if H is square. So the only way that this can happen is if you have a square matrix to begin with. Not every square matrix has an inverse, but every matrix that is invertible is square. Of course, rather than carry around an extra letter to denote the inverse of a matrix, we'll just use this notation that we're used to from functions and from other exponent things. So if the inverse of A exists, or if A has an inverse matrix, then we will call it A inverse, writing it like this, and we say that A is invertible. Of course, if A is invertible, then what is the inverse of the inverse? Well, you would probably expect that the inverse of the inverse should be A. And how could we check that? Well, just check if A satisfies the properties of the inverse of A inverse. So, right, the inverse of A inverse should satisfy this equation when you put your supposed inverse in here. Does A satisfy this equation? Well, yes, right, because A inverse satisfies the same equation. And then same thing on the other side, right? To find an inverse on the right for A inverse, what matrix would we have to put here? Well, it's A. You might also wonder, are inverses unique? Is it possible that A could have two inverses? So is it possible that A inverse is an A inverse and also, say, B is an inverse for A? Is it possible you could have two different inverses? Well, A inverse is equal to A inverse times the identity, because that's the definition of the identity, or a result of the identity. The identity matrix is, right, if B is an inverse for A, then the identity matrix we can replace with A times B, like this. But matrix multiplication associates, so we can move the parentheses over to here. But what is A inverse times A? That's the identity matrix of appropriate size, and what's I times B? It's B. So this shows that if you have two different inverses, actually they're the same thing. So really inverses are unique, which is probably no surprise.